All right, so welcome to Math 150 Multivariable Calculus. This is the third lecture. And what I'm going to do today is I'm going to actually give a lecture that I gave in Probability Math Stat 341, and also simultaneously in a mathematical biology class a couple of years ago, which is a really nice application of a lot of the tools and techniques that we're learning in Calc 1 and Calc 2, as well as Calc 3, as well as linear algebra, which is the class that comes next in the most natural progression. So one of the things I love to do is give you a sense of where do you go with all this? What do you do with the material that you're learning? How is it useful? And one of the biggest applications is to try to come up with models and to try to come up with ways to solve those models. You know, we can write down models, but can we find the answer to them? The next question, of course, is whether or not the model actually describes reality. And you know, the more accurate the model is, frequently the harder it's going to be to extract something useful from it. All right, so I'm going to quickly review some probability. I'm going to introduce difference equations and talk about how you solve difference equations. Difference equations are discrete versions of differential equations. So hopefully in Calc 1, Calc 2, you talked a little bit about solving some simple equations, you know, maybe y prime equals x or y double prime equals, you know, g or something like that. You know, you might have seen these in a physics class when you're trying to look at the kinematics equations, you know, where force is equal to mass times acceleration. Acceleration is the derivative of velocity. Velocity is the derivative of speed. So you get, you know, x double prime of t is, say, g if you have, you know, constant acceleration due to gravity. The difference between difference equations and differential is in difference equations, we have a discrete time step. So maybe we look at what happens every day or every year or something like that. And as time permits, I'll talk about some applications. One of my favorite applications is to Roulette, is to, you know, trying to, you know, use some of this stuff to gamble and try to estimate probabilities in the real world. All right, so it's just some background. So we've talked about this before, but a probability density is the following. So I have some random variable x whose values I care about. Maybe x is going to be, you know, the temperature, or maybe it's going to be how much money I win, just some quantity. And so the probability is going to be non-negative. P of x is greater than or equal to 0. The area under the curve is 1. And the probability I take on a value between a and b is just the area under the curve from a to b. So some of the more important items to use is the mean, which is going to just be the integral of x times p of x dx, if it exists. So this is the average value. When you talk about, you know, how you did, you know, in a semester, you know, if we have a discrete situation, maybe the final is 40%, midterm is 30%, homework is 20%, class participation, I guess would be 0 in this model, would be 10%. Then the way you would calculate your average would be 0.4 times your score in the final, plus 0.3 times your score in the midterm, plus 0.2 times your score on the homework, plus 0.1 times your class participation. And this would give you your average value. The next quantity is the standard deviation, or its square, the variance. So whenever you see something defined as sigma squared, it's a pretty good indication that the really significant quantity is the square root. So the variance is defined as the integral of x minus the mean squared times the probability distribution. And briefly, what the variance does is it measures how spread out you are about the mean. So if all of your mass is concentrated at the mean, or very, very close to mean, the variance would be 0 or close to 0. And the more spread out you are, the larger it's going to be. If you think about units, if x is in meters, if I ask you, you know, how tall is someone, you know, and you say, you know, they are, you know, 1.8 meters, you don't want to express your uncertainty about that in terms of meters squared. You know, meters squared, that's the unit of an area. You would want to express their uncertainty and their height in terms of, you know, meters. And that's why we want to look at the square root of variance. And then the last concept that we really need is that of independence. So knowledge of one random variable gives no knowledge of another. So to take a perfectly good example, which some people will disagree with, does your team's performance in a sporting event, is that affected by what shirt you wear when watching them on TV? Independent or dependent?
Independent.
Most people would say independent. You know, there's a lot of funny commercials, you know, trying to, just have some fun with the idea that it really does matter how you watch the game. It's also just fun to pretend, yeah, this is my lucky shirt. The team always does well when I wear this or I sit in that position. But there should be no causal connection between what shirt I wear and how my team plays, 100 or 1,000 miles away. And so one of the most important distributions in probability is the normal distribution. So it's defined as e to the negative x minus mu squared over 2 sigma squared, all divided by the square root of 2 pi sigma squared. So when you use notation like this, it's highly suggestive that mu is the mean and sigma is the standard deviation. So this should have mean mu and standard deviation sigma. And it turns out that that is the case. The big theorem in the subject, from Calc 1, Calc 2, the big theorem is the fundamental theorem of calculus. You can find areas by antiderivatives. The big theorem in probability is that if you have a bunch of independent, identically distributed random variables, so they all come from the same probability distribution, so maybe you're rolling a bunch of fair die, and you're just adding the values. If you add the values up, well, how large do you expect the sum to be? Well, if each one on average is mu and I have n of them, I would expect the sum to be n times mu. So I subtract off what I expect to be. The next is to try to figure out what's the correct scale to study things. And you want to basically divide by the standard deviation. And then we have to divide by the square root of n. That's a little bit more complicated as to why it's the square root of n. It really comes down from taking the square root of the variance. The variance is going to have n terms. I really don't want to get into that. It turns out that this is going to converge to being normally distributed, to having a normal distribution with mean 0, variance 1. We will talk about logarithms later. There are a couple of log laws. The log law people forget the most is the change of base formula to convert from log base b to log base c. One of the reasons the change of base formula is so important is it means you only need to calculate logarithms in one base. And once you have them in one base, you have them in every base. We're doing something very similar here. When we're trying to measure something, we convert everything to what's called the standard normal, the mean 0, variance 1. This is a really powerful concept. So it means we only have to tabulate probabilities and understand the behavior in tabular form for this one curve. So as an example, let's look at a uniform random variable. So it has a density that's 1, or that's constant. All values are equal in a certain range, and then the probability is 0 everywhere else. And I've adjusted it so that it has variance 1. And so you can see the blue is the uniform random variable. Its probability is a little bit less than 1 because it's going from almost -2 to 2, and I need the area under it to be 1. And I've superimposed on it, the standard normal. And you can see it's okay, but it's not really that good of a fit. If I look at the sum of 2 uniform random variables, adjusted so that the standard deviation of the sum is 1, you can see it's a nice triangle function. And this relates to what we talked about with rolling die. If I roll 2 fair die and I look at the sum, I can get 2 or 12 only 1 out of 36 ways. I can get 7, 6 out of 36 ways. And it's a nice linear going up, linear going down. And you can see, that triangle is not so bad in terms of looking like the normal. If I look at 4, it looks pretty close, and you can begin to see the curviness. Why do we do 4 and not 3? Well, because if I do 4, I can just look at the sum of 2 plus the sum of 2. And that just makes things a little bit easier. So after looking at 4, what do you think we should look at next?
8.
8, excellent. It's much better to just keep doubling. And this is a really good theme in mathematics, that often if you just double, then you can just take what you had and just do it again. 8 would be a lot easier to look at than 6. With 6, I would have to do 2 3s or a 4 and a 2. And with 8, you can see it's getting even closer. Now, one of the big themes, and this is different than what you've seen in earlier math classes, is that the further you go, the harder it is to get an exact answer. So the blue curve is our actual answer. The gold curve is the standard normal. Here is an explicit formula for the density of a sum of 4 uniform random variables. And the definition depends on where you are. It has several different components. If you want to work with this, you need help. There's no nicer way to put it. This is not pleasant to work with. It's exact, but it's painful. You have so many different regions, you have so many different constants and whatnot. It's much easier to say, oh yeah, it's approximately a standard normal. And the standard normal is very easy to work with. If you want for extra credit, calculate what you would get if you had the sum of 8 random variables that were all uniform. And if you're interested, I can help you figure out how you would actually do a calculation like this. It is exceptionally painful. So we want to try to come up with models that we can work with. And the real big idea is sometimes rather than solving the problem, we just want to approximately solve the problem. If you think about the airlines, imagine you own American Airlines. What is your objective as the CEO of American Airlines? Who's one of my econ majors? What's your objective if you own American Airlines? So can somebody tell me what should be the objective of American Airlines?
Maximize profit.
Make money, maximize profit, right? Their objective is not to fly people. How do they make money? Probably by flying people. But their objective is to make money. And so there are some routes that, not enough, maybe a lot of people want to fly them, but they're not willing to pay how much it would cost the airline to do them, so the route's not profitable enough. So you always want to figure out what is your objective. We have some powerful techniques to solve optimization problems like this, to figure out what the airline schedule should be. The problem is the problems are so complex, we can't come up with an exact solution, but we can get very close to the correct solution in a very short amount of time. If you're talking about numbers on the orders of billions of dollars, and you can be within $10,000, that's close enough for all practical purposes. So what I want to do is I want to talk a little bit about different equations first. So there, as I said, a discrete version of differential equations, you have time increasing in increments of, say, 1 unit. And so I have some term an is going to be a function of the previous terms. And I'm going to consider just the special case when it's a function of a fixed number of previous terms, the L terms before, and it's always the same relation. So one of the most famous examples is the Fibonacci's. Fn is Fn minus 1 plus Fn minus 2. And it's not enough to just write down the relation. You also need to give the initial conditions. And so once I give you the first 2 values of the Fibonacci's, if each one is the sum of the previous 2, once I know 0, 1, what's the next number?
1.
1. And what comes after 1?
2.
2, then 3, then 5, then 8, then 13. So once I have 2 values, everything is determined. Now, it could take a while to compute, if I want to go to the millionth or the billionth or the trillionth, but I can get there. So we will often look at what's called constant coefficient fixed depth. So that means the coefficients in front of the a's do not depend on the index n. They're independent of n, and we only go to a certain depth. We only consider L terms. So as I remarked, we can compute, but it could be expensive if you want to go down a million, a billion, or a trillion. So hopefully you've seen a little bit on matrices. You do a lot more with matrices and linear algebra. I'm going to just do a little bit right now as a motivation for what comes next. We will talk about matrices and vectors in this class, so it's worth just seeing a little bit about matrices. And so matrix takes a vector and gives you a new vector. If it's a square matrix, it gives you a vector that has the same dimensions. So if you had a vector with 2 components before, you still have a vector with 2 components. And so it turns out I can write my vector, my Fibonacci vector Fn plus 1 Fn as the matrix 1, 1, 1, 0 acting on Fn, Fn minus 1. And this just goes back to how a matrix acts on a vector. So hopefully you've seen this in trying to solve systems of equations. If not, I and the TAs are happy to talk to you. This is going to be covered in great detail in linear algebra. We're not going to do too much with this in the class, but I just wanted to make this there so you can see what comes next. So this leads to a matrix formulation of the Fibonacci problem. So I'm going to let Vn be the vector Fn minus 1. Vn plus 1 will be the vector Fn plus 1 Fn. And so Vn plus 1 is equal to AVn. And now what we're going to do is what I call shampoo mathematics. Has anybody ever read the instructions on shampoo? How are you supposed to use shampoo? Anybody know? Makes me a little concerned about hygiene here. So shampoo instructions say lather, rinse, repeat. So what you do is you just keep repeating the process. If Vn plus 1 is AVn, well then Vn would be AVn minus 1. And so that becomes then Vn plus 1 is just going to be A squared Vn minus 1, or A cubed Vn minus 2, and you go all the way down to An V1. I always get confused as to just what is the last index supposed to be. We see when we have A Vn, we have 1 power of A, we have an index of n that adds up to n plus 1. The next one was we have A squared, we have Vn minus 1, 2 plus n minus 1 adds up to n plus 1 again. Okay, so when we go all the way down, we get to n for the power of A, so the index of V should be 1. So what this tells us is if we give you the initial Fibonacci numbers, the 0 and the 1, we can calculate the nth one by just looking at a high power of a matrix. And then it turns out that you can actually use linear algebra to solve and find out what is the effect of high powers of matrices. So I'm not going to discuss any of this right now, but this is just one of the advantages of linear algebra. It leads to explicit formulas like the one below, and you can then actually extract a closed form expression for the nth Fibonacci number. 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. So 1 plus root 5 over 2 is the famous golden mean. What I love about this formula is what kind of numbers are the Fibonacci's? 0, 1, 1, 2, 3, 5, 8, 13. What kind of numbers are these?
Whole numbers.
Whole numbers. When you look at this, does this look like a whole number? We've got divisions. We've got square roots, yet miraculously everything cancels and you get a whole number. All right, so let's do an application of this. Why might we care? So let's say we want to model population of whales, and I will give extra credit. You're not allowed to Google or you do any kind of web search. What movie involves bringing forward in time 2 humpback whales named George and Gracie to repopulate the species? So if you can get that, just email me for cultural extra credit. So let's assume, and these are perhaps maybe a little bit strong assumptions, and we'll talk about that in a moment, that whales always die when they turn 4, never earlier. Each pair of whales becomes pregnant when they turn 1 and gives birth to 2 pairs of whales when they turn 2, so 1 year later. And then each pair becomes pregnant when they turn 2 and gives birth to 1 pair of whales when they turn 3. Can we figure out how many whales there are of each age at each moment? Of course. As long as I tell you how many whales there are of each type, I have rules that tell me how many new whales will be born and how many whales will die. So it's a very simple deterministic process. That doesn't mean I can immediately tell you how many whales there will be 1 million time steps from now. It might be very hard to do that, but in principle, I can just keep iterating. So we're going to set up a system to describe the population. So let's let AN be the number of whales that are, a number of pairs of whales, it's easier to work in pairs, that are born in year n. BN will be the number of pairs that are 1 year old in year n. CN will be the number of pairs that are 2 years old in year n. DN, the number that are 3 years old in year n. And we want to figure out what AN plus 1, BN plus 1, CN plus 1, DN plus 1 will be in terms of A, B, C, and DN. So can anybody tell me how many whales will there be 1 year old in year n plus 1? What would BN plus 1 be? In terms of the ANs, BNs, CNs, and DNs, if I want to know how many whales are 1 year old in year n plus 1, BN plus 1, what would that be?
That would equal AN.
That would equal AN, because everybody that was born in year N becomes 1 year older. And we're assuming no wheel dies before they're 4. So how many wheels would there be of that are 2 years old in year N plus 1? What would Cn plus 1 be?
Bn.
Bn. And so we just get the formula as listed, Dn plus 1 will be Cn, and the more interesting one is An plus 1 is just going to be 2Bn plus Cn. And so we can write this down in a little bit more illuminating manner. So An plus 1 is going to be a function of An, Bn, Cn, Dn, same for the others. And we can put this into matrix form. So An plus 1 is going to be 0, 2, 1, 0, and so on, so on, and so on. And very similar to the Fibonacci's, we can just say, well, how many wheels we have at time n plus 1 is just a to the n plus 1 times the initial conditions, A0, B0, C0, D0. So if we can understand high powers of matrices, we can actually solve this problem. So is this form reasonable? What properties does this have? So I'm not going to go through and talk about solving it. I'm going to just ask right now, does anybody have any concerns? Anybody with any biological intuitions about what might be problematic with this model? So all wheels live to 4. They don't die earlier. They don't die later. You give birth to 2 pairs of wheels at one time, 1 pair of wheels at another time. Any concerns about these assumptions?
I mean, they're not realistic.
Okay, so which one is not realistic and why?
Like, not all whales live the same number of years, and not all of them give birth to the same number of whales.
Yeah. You might have on average this is the case, but it seems unlikely that every wheel. Now, if you have a tremendous number of wheels, things might approximately average out. But in the beginning, a little bit one way or the other can make a huge impact. So, these are not reasonable assumptions. The other thing is, it's assuming that we have infinite resources, that, as the wheel population is exploding, there's going to be plenty of food for them and plenty of space for them. They're not going to be interfering with each other. So there's a lot of problems with this model. And so what's the solution? Well, one possibility is we could introduce some random variables. So S1, S2, and S3 are going to be random variables about the probability that you live to the next year. And when you're young, maybe the probability is high, but as you start to get older, the probability is going to start to get smaller and smaller. And similarly, we can play with how many wheels are produced. And now what this means is we're going to have to understand products of matrices. And so again, this becomes a lot of fascinating modern research is trying to understand what can you say about products of random matrices. It turns out, unfortunately, that products of matrices are very difficult. The real reason I want to talk about this now, we're not going to do much about this. I know we have a couple of people here who are considering a career in physics, and in physics, you do look at the exponential of matrices. And so because of that, I want you to have at least seen something now. So I will try to throw into the semester topics related to what people are interested in. You do not need to make sure that you understand every topic. Special things like this are not going to be on exams. This is to just give you a sense of where things go. We know the formula for e to the x is the sum of x to the n over n factorial. There's nothing that says x has to be a real number. You can put in a matrix and you can calculate e to a matrix. Well, what is e to a matrix? Well, as long as the matrix is square, we can calculate a squared, a cubed, a to the 4th, and the following sum makes sense and it actually converges. And so you can talk about e to the a. This becomes extremely important in quantum mechanics in terms of solving certain equations. So if I give you 2 matrices A and B, you might guess that e to the a plus b is e to the a times e to the b. After all, e to the x plus y is e to the x, e to the y, when we have real numbers. Unfortunately, this is not true when you have matrices. And the reason is matrices commute. And so I defined something on the previous page. I didn't really emphasize it. I'm going to go back and talk about it now. The commutator of two matrices is AB minus BA. Well, if A and B are just real numbers, then that's going to be 0. But in general, if I have two matrices, matrices typically don't commute. And so AB minus BA is typically not going to be 0. This is called the Baker-Campbell-Hausdorff formula as to what is e to the a plus b. And you can see it's a god-awful mess. We can write it down, but it involves commutators and commutators of commutators and commutators of commutators of commutators, multiplying everything together. Okay. I want to talk to you very briefly about efficient calculation. And this is going to lead into some of the stuff for later in the semester. So the real split between Math 150 and Math 151 is Math 150 assumes that you have not done Taylor series and sequences in series. Math 151 assumes that you have and does the Green-Gauss-Stokes theorems. Green-Gauss-Stokes are absolutely essential for doing electricity and magnetism. And so I will make sure we have at least one lecture on that. But for those of you who want to do physics, who want to make sure you've done plenty, I'm happy to just have some extra classes and talk a little bit more about that, or work some of that into the semester as I can. So I'm going to talk about Binet's formula and different ways to prove it. The first is the method of divine inspiration. So let's say we have the Fibonacci numbers, Fn equals Fn minus 1 plus Fn minus 2. And I want to try to come up with an explicit formula for the nth Fibonacci number. Well, one thing is to try to build some intuition. What's going on? I'm adding the two previous terms. Well, if I start off with positive numbers, then my sequence is going to be getting larger. So for the Fibonacci's, it goes 0, 1, 1, 2. Okay, but if I just start with 1, 2, I can see it's always going to be getting larger from that point onward. It's definitely not going to be getting smaller. So what I can do is I can say, well, if I replace Fn minus 1 with Fn minus, if I replace Fn minus 2 with Fn minus 1, I've made the right-hand side either larger or kept it the same. If I replace Fn minus 1 with Fn minus 2, I've made the right-hand side either the same or made it smaller. So we get that Fn is sandwiched between twice Fn minus 2 and twice Fn minus 1. What does this mean? It means every time I increase my index by 1, my Fibonacci number at most doubles. And another way of looking at it is every time I increase my index by 2, I at least double. Or equivalently, every time I increase by 1, I at least increase by the square root of 2. And so this suggests that the nth Fibonacci, well, actually it tells us that the nth Fibonacci number is going to be at most 2 to the n and at least square root of 2 to the n. So we see that there's a geometrical and exponential relationship going on here. We have exponential bounds. It's at least square root of 2 to the n. It's at most 2 to the n. Let's try Fn equals r to the n. Let's just guess that the nth Fibonacci number is just r to the n. And we can use this to get Binet's formula. I'm going to show you another way, which is going to motivate some of the stuff later in the semester. So what we're going to do is we're going to take the recurrence relation. I'm going to write it this time as Fn plus 1 is Fn plus Fn minus 1. And I'm going to write down what's called the generating function. So I'm going to look at this sum, the sum of Fn x to the n. So one of the big themes of the last unit of the semester is going to be sequences in series. When does the sum converge? It is essential, or at least I think it's essential, to explain to students, why are we spending time on this? We only have so much time in the semester. Why are we going to spend so much time talking about when do sums converge? Well, one of the reasons is there are powerful techniques to analyze things by forming sums related to them. And so what I'm doing is I'm taking a bunch of information, the fn's, and I'm bundling it together into what's called a generating function. And it turns out I will be able to come up with a closed form expression for this function g of x. And from that, I can use that to get a closed form expression from Fn. This almost seems like magic. We start off with the Fibonacci relation, we have these fn's which we don't know explicitly. We bundle them together, we get this infinite sum, and somehow from that we deduce exactly what they are. Well, you have to think about it carefully. Once I tell you the recurrence relation, we actually know everything in the world about the Fibonacci numbers. It's just how do we extract that knowledge in a useful way? So I'm defining g of x to be the sum n greater than 0 of fn x to the n. I can start off with n equals 1 because we're letting the 0th Fibonacci number be 0. So we're going 0, 1, 1, 2, 3. So let's look at what's going on. So let's just look at the sum from 2 to infinity of fn plus 1 x to the n plus 1. Well, I use the Fibonacci relation that fn plus 1 is just fn plus fn minus 1. And I'm not going to worry about justifying all the stuff here. That's what we can do later in the semester when we do sequences and series. Right now, just enjoy the show. Everything can be justified. The sum can split into two different sums. And in the first one, I have fn x to the n plus 1. Well, the index of f is not quite the same as the exponent. So why don't I just pull an x outside of that sum so that they'll be the same? For the next one, I have fn minus 1 and xn plus 1. The exponent is not the same as the index. How many powers of x should I pull out of the second sum? So I want the power of x to be the same as the index. So for the first one, I had fn x to the n plus 1, so I pulled out an x. What should I pull out for the second one?
X squared.
X squared. And so when I do that, I'm first going to just clean up the summations. And then I'm going to pull out the x and the x squared. And so when you do the algebra, you get the sum of fn xn from 3 onward is x times the sum from 2 onward plus x squared from the sum 1 onward. Well, I want all of my sums to start at 1 because then it's going to be the same function. It's just going to be g of x. So for the first one on the left, I just have to add on the terms of n equals 1 and 2 and subtract them. And then for the first one on the right, I have to add in the term when n equals 1 and subtract that. And so when I do, I get the left is g of x minus f1x minus f2x squared equals x, g of x minus f1 of x plus x squared g of x. I can now solve, and I get g of x is x over 1 minus x squared. So we now have g of x is x over 1 minus x squared. What is your least favorite technique of integration? If you don't answer what I'm thinking of, it's because the technique was so traumatic, you forgot you learned it. Of all the techniques, which one makes you cringe the most when you see you have to use it? Anybody have a least favorite integration technique?
Integration by parts.
Nope.
Trig substitution.
Nope, there's something much worse than both of those.
Riemann sums?
I'm sorry? No. Because we only use Riemann sums to prove the fundamental theorem of calculus. We don't actually use it to integrate. There's another method of integration. Anybody remember other methods of integration? There's U substitution, there's integration by parts, there's trig substitution, there's one other one. Just seeing if anybody remembers this one.
Is it the partial fraction decomposition?
It is the partial fractions. This is the ones that people hate typically the most. So partial fractions are actually useful. So if we do a partial fraction expansion, what we can do is we can write 1 minus x squared in the following way on the right-hand side. And now if you look at the denominator is 1 minus something times x, 1 minus something times x. This looks a lot like the geometric series. 1 plus r squared plus r cubed plus r to the 4th plus r to the 5th. This is 1 over 1 minus r. So hopefully you've seen this before. If not, we will see this later in the semester. An infinite geometric series converges if r is less than 1. So if x is sufficiently small, I can expand each one of these as a geometric series. And that's then going to lead to the closed form expression for Fn. And so again, we're just using the geometric series formula. So this is a really nice application of partial fractions. If I now want to compute the millionth Fibonacci number, I don't have to go through all of the earlier ones. I can just jump straight to it. And again, what I'm trying to do here is just show you what are we going to be learning in Calc 3? Why are we going to spend time learning this? It's nice to have an explicit formula like this. It's nice not to have to calculate all the stuff beforehand. And if I just care about where am I a million years from now, to just jump to that value. All right, and it allows us to do many properties. I'm not going to really go into that now. And so what I want to do is I want to do an application. So just because this is being recorded, I have to be very careful and say, I am not advocating that you use any of this to go and gamble, nor does Williams College. If you go gambling, you will do so on your own choice. The mathematics that I'm going to teach you today will not help you successfully gamble. In fact, the goal is to show you why you should not be doing certain things. So we talked earlier about the purpose of American Airlines. Imagine you are a casino owner in Las Vegas. What is your objective?
Get people to gamble.
Close. What is your objective as a casino owner?
Make money.
To make money. How do you make money? You get people to gamble. Do you think the games are structured to favor Las Vegas or the person gambling?
Vegas.
They're structured to favor Vegas. The expression is someone has to pay for Mr. and Mrs. Smith's suits. Yeah, the money for these salaries and all of this extravaganza has to come from somewhere. And a lot of it comes from people not understanding mathematics. And so one of my favorite games is Roulette. And so, the way Roulette works is you have a bunch of numbers, some red, some black, and you have 2 greens, 0 and double 0. And you can bet that the ball, when it goes around the wheel, is going to stop on either a red, a black, or a specific number. If you bet on a specific number, obviously you will make more money than if you just bet on red or black. There are 38 numbers, 2 greens, 18 reds, 18 blacks. Approximately, what is your chance if you bet on red that it's going to come up red? Approximately.
A little less than half.
A little bit less than a half. And so that little bit less than a half is going to greatly help Vegas. If you want, we could assume a nice world where Vegas decides that they don't want the advantage of the greens and we'll make it exactly a half. So we will assume that you have a 50-50 chance. And now here's a strategy that a lot of people use. It's called double plus 1. And the way it works is the following. You bet $1 on red. If it comes up, you win $1, great. If not, you're down $1. So if you're down $1, what do? Now you bet $2 on red. If it comes up red, you've won $2, you had lost 1, so you're net $1. If not, you're down 3. So now you bet $4. If it comes up red, you win 4, you've lost 3, you net $1. If not, you're down 7. So what happens? Bet 8. If it comes up, you net $1. If not, you're down 15. And then we just do shampoo mathematics. Eventually, it's going to come up red. Eventually, we would net $1, lather, rinse, repeat, and you can make as much money as you want. As much as I love teaching, if this was a really good idea, do you think I would still be teaching at Williams College? Or do you think I would have made my millions and gone to some Caribbean island? Is there an issue? Or do you think I just love teaching this much? You are a wonderful group of students, as are your predecessors, and as will be your successors, I'm sure. Do you think there must be something wrong with this method? If not, you should be planning to go to Vegas or Atlantic City or some casino very quickly. Do you think that there's probably something wrong with this?
Has to be, I
Yes.
guess.
Yes. Okay, can anybody think, there's actually two issues with this method. Can anybody think of either issue with this method?
Well, it only works if you've like infinite money, like
Yes.
eventually.
Yep. So you need infinite money. So what I'm going to do, for instance, if we do this a couple of times, at one point you might have to bet over $1 million. And most of us may not have $1 million liquid. If you do, please talk to me after class. So what I'm going to do is I am going to make an unreasonable assumption. So for those of you in economics, this should be okay. You should be used to this by now. I'm going to have the eccentric rich aunt-uncle hypothesis. So I hypothesize that I have an extremely rich, crazy member of my family who is willing to bankroll me. Whatever amount of money I need, they will ensure that I have. But they will not give me $1 directly. But if I need any money, they will give it. So if I need $1 million, they will give me $1 million. So you don't have to worry about having $1 million. Okay, this is extremely unreasonable. If I can show you that even in this unreasonable situation, we don't lose money, then you know the method is flawed. There is another issue, but you need to know a little bit more about how Vegas does roulette. Does anybody know the other issue? So for this, oh, sorry, yes.
I was just gonna say, even in the best case scenario, you're not making very much.
Well, but
To, like,
that's,
cover
that's
whatever.
fine. That's fine that I'm not making very much. I can just keep iterating. Or instead of betting, $1 initially, I bet 100 or 1,000 or $1 million initially. And now rather than winning $1, I win $1,000 or $1 million. So I can scale it up. So the issue, you need to know a little bit more about how roulette is done in Vegas, is what's called table limits. Is often each table has a maximum and a minimum bet. And this is calculated very carefully. Maybe the table limit is $150. And so I've just lost 7 in a row, and I want to bet 256, but that's above the table limit. So the problem is when you win small. And when you lose big. So the question then becomes, well, what's the probability that I get, say, 7 blacks in a row, or 5 blacks in a row, or 6 reds, or whatever? So let's say we're betting on red. So if we get 5 blacks in a row, that's going to make us bankrupt. So let's let Pn be the probability we will not get 5 consecutive blacks in n spins. Because if we get 5 consecutive blacks, we exceed the table limit and we're done. Well, if Pn is the probability we will not get 5, let Qn be the probability we will get 5. So clearly Pn plus Qn has to equal 1. They're complementary events. And this is one of the big insights in probability. Sometimes, rather than computing the probability that something happens, it's easy to calculate the probability something doesn't happen, or vice versa. And it's not always clear which one is the easier one to compute. So it turns out it's going to be easier to compute the probability we will not have 5 consecutive blacks in n spins. So let's start off with n spins. So Pn is the probability we do not have 5 consecutive blacks in n spins. For the first spin, and we're going to take the very nice case that there's no greens, we have a 50% chance of spinning a black, a 50% chance of spinning a red. If we spin a red, could that start a streak of 5 consecutive blacks? No. So here's the first tough question. What is the probability we do not have 5 consecutive blacks in n spins, given that the first spin is red? So Pn was the probability we don't have 5 consecutive blacks in n spins. Now we know the first spin is a red. How many spins are left?
Four.
I'm sorry?
There's 4 left, and that's not enough to get
Oh,
5
no,
consecutive blacks.
hold on. We have to do n spins. We've spun once. So how many spins are left?
n-1.
n-1. So what's the probability we don't have 5 consecutive blacks in n-1 spins, because the first spin was a red and is not going to count to a string of blacks? what's that probability going to be?
Pn minus 1.
Pn minus 1. And so now that's going to be Pn minus 1. So now we look on the other side where we had a black. So on the next spin, we could get either a black or a red. Well, if we start off black, red, which happens with probability 1/4, could that be the start of 5 consecutive blacks? No, because it goes black, red. It can't be 5 consecutive blacks. So if we start off black, red, how many spins do we have to do to get up to n spins? How many spins are left to do?
N minus 2.
N minus 2. So what's the probability that we do not have 5 consecutive blacks, given that we start off black, red?
1 minus Pn minus 2.
No, it's just Pn minus 2. Because Pn is the probability we don't have 5 consecutive blacks and n spins. So it's just going to be Pn minus 2. And so if we keep going, if we do this, 5 times, if we go black, black, red, the probability we don't have 5 consecutive blacks, but we'd have n minus 3 spins left. That'll just be Pn minus 3, then Pn minus 4, then Pn minus 5. Why have I stopped? Why am I not doing one more spin? I'm trying to calculate what is the probability I don't have 5 consecutive spins that are black. Why am I not doing the next level? So if you look at where we are, what have our first spins been at this point? It's been black, 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 black. How many spins in a row do we have that are black?
You have the 5 we're looking for.
We have 5. So once you have 5 spins in a row that are black, what is your probability that you don't have 5 consecutive blacks? It's going to just be
0.
0. And that's why it's easy to calculate Pn, the probability that it doesn't happen, because the tree ends here. We don't have to keep going. And so it turns out we get a recurrence relation. The probability we end up with, just the red for the first spin is 1/2. Then we go black, red is 1/4. Black, black, red is 1/8. Black, 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 red is 1/16. Black, 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 red is 1/32. And so we can get a recurrence relation. And I'll just jump ahead. Pn, the probability we don't have 5 consecutive blacks and n spins is just 1/2 Pn minus 1 plus 1/2 squared Pn minus 2 and so on. This is very similar to the Fibonacci equation. It turns it's also very similar to the Wheel equation. It's a difference equation. It's of finite length. It has coefficients that are independent of n. And it turns out we could either write down in closed form what the answer is, or we can just go in even Microsoft Excel and just start off with a couple of initial values and see what happens. If we have 1 spin, what is the probability you don't have 5 consecutive blacks if you only spin once? So if we only have 1 spin, what's the probability we don't have 5 consecutive blacks?
1.
1. And so, P0, P1, P2, P3, P4, the probabilities we don't have is all going to start off as 1. And so it turns out when you try to do this, the initial conditions, as I remarked, are all equal to 1. And you can then just feed this in. You can use Mathematica. You can plot it. And so if you want to plot the probability that we have 5 consecutive blacks in 100 spins, it's actually 81%. So 81% of the time, if you were to do this 100 times, you would get 5 consecutive blacks at some point. If you do 200 times, it's 96.59%. The probability converges to 1 very quickly. And this is something that people who try to use this method do not understand. Most people don't see that it's actually quite likely that you will hit the table limit very quickly. If I ask you to give me a random sequence of tosses of coins, heads and tails, most people know you should have approximately the same number of heads and tails. But what a lot of people don't know is what should be the longest run of heads and tails. And that's exactly what we're calculating over here. And you can very easily, if you know advanced mathematics, tell if somebody actually is just flipping the coin honestly, or they're just making things up. And again, you can simulate this. You can just show that all this is true. I'm not going to go into the Zeckendorf stuff. I just want to end with just saying that this is a nice way to see some of the applications of what we're doing. Is we're looking at these sequences in series. This is going to be a big theme of the class. We want to try to figure out, what's going to happen. So we want to come up with a mathematical model. The simpler the model is, the greater chance we have of solving it. The more complex it is, the harder it's going to be. We're going to see this time and time again during the semester. And we're going to use tools from calculus. And as you go further in math, you get more tools. You get the tools of linear algebra. You get the tools of probability theory. And not surprisingly, the more you do, the more you can say. All right, this is a good place to stop. I will